what are you hoping? I understand that you are the lead scientist for the James Webb Telescope, and that's about to launch. And what are you really hoping you will understand from that launch and subsequent research and information sent back there?
And what I really hope is that we'll get a big surprise out of our new observatory, because that's always happened every time we built a new great observatory. Something that nobody ever guessed was out there would happen. So it's a reminder that our imagination, no matter how feverish we might feel, is still limited, and we don't usually guess what nature has done.
Picture yourself drifting in an endless sea of darkness. Around you is our galaxy, the Milky Way, a brilliant swirling metropolis of light. For the better part of a century, we've held a core belief about our universe, that on the grandest of scales, it's pretty much the same everywhere. This is the cosmological principle, a pillar of modern science. But what if that pillar is cracked? What if our cosmic address isn't in a bustling, typical neighborhood, but out in the vast, quiet countryside? Sounds like science fiction, right? Well, it might actually be closer to the truth of our existence than we think. An idea that was once on the fringes of astronomy is now getting a serious second look, all thanks to the most powerful space telescope ever built. The James Webb Space Telescope hasn't delivered a final verdict, but its powerful eyes are providing tantalizing new clues in the case for one of the most unsettling ideas in science: the possibility that we are living inside a gargantuan cosmic void. So why does this matter? To grasp how revolutionary the idea of living in a void is, you have to understand the picture it's trying to replace. The guiding light for astronomers has been the cosmological principle. It basically says the universe is homogeneous and isotropic on the largest scales. In other words, no matter where you look, it should appear more or less the same. There's no center, no edge, no special spots. Think of it like being in a massive forest. Right around you, you see individual trees, clearings, and dense patches. But from an airplane, the whole thing just looks like a uniform carpet of green. The cosmological principle assumes the universe is like that green carpet. Our local group of galaxies is just a small clump of trees, but on the scale of billions of light years, it all averages out. This wasn't just a hunch. The strongest evidence came from the cosmic microwave background, or CMB. This is the faint, leftover heat from the Big Bang, and it's everywhere. When we map the CMB, it is shockingly uniform. This smoothness was taken as proof that the early universe was incredibly even, forming the bedrock of our standard model of cosmology, lambda CDM. This model has been a wild success, explaining almost everything from how galaxies form to the expansion of the universe itself. It tells a story where denser regions of an early primordial soup slowly pulled in more matter, creating the great cosmic web we see today, glittering filaments of galaxies connecting massive clusters. And in between those filaments, voids. The standard model predicts them, but it is always assumed that we live on one of the filaments, the typical part of the cosmic web. For decades, that was our address. But then astronomers started noticing things that just didn't add up. The first clues that our cosmic neighborhood might be a bit weird started popping up decades ago. In the 70s and 80s, astronomers began mapping the 3D positions of galaxies and found something shocking. The universe wasn't smooth at all. It was clumpy, with galaxies arranged in huge walls and filaments that surrounded enormous, almost empty regions. The most famous of these was the Boötes void, found in 1981. This wasn't just any gap, it was a mind-bending 330 million light-years across, a region so empty that if we were in the middle of it, we wouldn't have known other galaxies even existed until the 1960s. Its scale seemed to defy the standard models. As our maps got better, we found more voids. They're like the air pockets in a cosmic sponge, making up most of the universe by volume. But the assumption remained. We live on the sponge, not in the holes. That is, until a more direct challenge came from a team of astronomers, including Amy Barger. They analyzed data from multiple sky surveys and found our local patch of the universe seemed to have way fewer galaxies than average. They proposed we weren't just near a void, we were inside a colossal one, maybe 2 billion light-years in diameter, which they named the KBC void. This was a radical idea. It suggested our location is special and that our view of the universe might be skewed. For many, this felt like a step backward, a return to a pre-Copernican idea that we're at a special place in the cosmos. But the void hypothesis offered an elegant solution to an even bigger problem that was brewing in cosmology. That crisis is called the Hubble tension. It's a persistent disagreement over a single number. How fast is the universe expanding? The problem is, we have two main ways to measure it, and they give us two different answers. The first method looks deep into the past. By studying that baby picture of the universe, the cosmic microwave background, and using our standard model, scientists predict the expansion rate today should be about 67 kilometers per second per megaparsec. The second method measures the expansion rate locally. Astronomers use standard candles like Cepheid stars and supernovae to measure distances to nearby galaxies and see how fast they're moving away from us. This method consistently gives a higher number, around 73. The gap between 67 and 73 is not a fluke. The measurements are now so precise, their error bars don't overlap. It means one of three things. Our understanding of the early universe is wrong, our local measurements are wrong, or the model that connects them is broken.
This is where the void hypothesis comes back in. What if we live inside a giant, underdense bubble? The theory suggests that the denser regions surrounding this void would have a stronger gravitational pull. This extra tug would pull galaxies inside the void, including us, toward the denser edges. This local movement would add to the overall cosmic expansion, making it look like our local universe is expanding faster than the global average. It suggests the Hubble tension isn't a crisis at all, but a local environmental effect. Our cosmic speedometer is reading high because we're measuring from inside a valley. But how could you ever prove you're stuck inside a forest? You'd need a new set of eyes, something powerful enough to map the whole landscape. And that detective is the James Webb Space Telescope. Webb is a machine designed to see the universe in a completely new light, infrared light. As the universe expands, it stretches the light from distant galaxies into the infrared spectrum. Webb's giant golden mirror is designed specifically to capture this ancient, faint light, allowing it to create the deepest and widest maps of the cosmos ever attempted. This is exactly what you need to test the void hypothesis. To know if we're in an underdense region, you need an accurate galaxy census. Now, has Webb pointed its mirror at the sky and declared, "Case closed, we live in a void"? Not yet, but what it is doing is providing the most pristine, high-definition data to test this very idea. A huge project called Cosmos Webb is dedicating hundreds of hours to mapping a massive patch of sky, cataloging up to 1 million galaxies. The early images are staggering, revealing the cosmic web in breathtaking detail, bright filaments of galaxies separated by vast, dark expanses. These maps will allow scientists to compare our local galaxy density to the cosmic average with unprecedented precision. At the same time, Webb is also sharpening the Hubble tension itself. Some hoped the problem was just errors in our local measurements, but Webb's new observations of Cepheid stars are so precise they've confirmed the local measurement of 73, reducing the likelihood that it's all just a calibration mistake. In a way, Webb has increased the pressure to find a physical explanation. It has made the void hypothesis a more necessary and compelling line of inquiry. So, let's just entertain the idea for a moment. What if the evidence continues to build, and it turns out we do live in a giant cosmic void? What would that actually mean? First, the Hubble tension, the biggest crisis in cosmology, would simply evaporate.
There would be no need to invent exotic new physics to explain it. The standard model of cosmology would be saved with one big asterisk. Our measurements are subject to local environmental effects. We would have to accept that to understand the universe as a whole, we first have to account for the quirks of our own backyard. The cosmological principle, the idea that we're in an average place, would be shown to be an oversimplification. Beyond the numbers, this would have profound philosophical implications. Science has always moved us further from the center of things, but the void hypothesis reintroduces a strange kind of specialness. We wouldn't be at the center, but we would be in a uniquely empty, quiet place. Could this be the reason we're here? Are we truly alone, or is our isolation part of a grander cosmic design? In a denser, more typical region of space, disruptive events like nearby supernovae or galactic mergers are more common. Perhaps our quiet corner of the cosmos provided a sheltered harbor, a stable nursery where life could take hold and flourish over billions of years. Our cosmic loneliness might be the very reason we are here to ponder it. It's a humbling thought that forces us to reevaluate our perspective, a reminder that we are looking out at the universe from a valley, not a mountain peak. The James Webb Space Telescope hasn't closed the book on this mystery. If anything, it has thrown the doors wide open. It's giving us the sharpest tools yet to investigate, and its initial findings are only deepening the intrigue. The data is confirming the fundamental filament and void structure of the cosmos with stunning clarity, while at the same time solidifying the very tension that a local void could solve. The ultimate confirmation remains over the horizon, buried in the terabytes of data Webb is sending home. Scientists are meticulously building that definitive census of our local universe, looking for the statistical proof of a deficit and for the telltale signs of galaxies flowing away from us. This is science in action, a cosmic detective story playing out on the grandest possible scale. So, are we adrift in a great cosmic nothingness? Is our loneliness the secret to our existence? The final pages of this mystery are still being written, and as Webb's golden eye continues to stare into the deep, we wait for the evidence that could, once and for all, rewrite our place in the universe. What do you think? Does living in a void seem like a plausible explanation for the Hubble tension, or is there something even stranger going on? Let me know your thoughts down in the comments, and if you want to stay on the cutting edge of these cosmic discoveries, go ahead and smash that subscribe button so we can float through the emptiness together. Until next time, keep looking up.